For most of your life, you were told Earth is special. But the latest telescopes quietly suggest something else. Earth might not even be one of the best places for life in our own galaxy. For decades, we treated our planet as the gold standard, the benchmark, the model the universe would copy. But the new data doesn't support that story. It whispers a stranger, more uncomfortable one. Out there are planets that outperform Earth. Worlds with gentler climates, richer atmospheres, quieter, steadier suns, and billions more years for life to evolve. If that's true, then our home may not be ideal. It may just be average. And that leads to a question most people never ask. A question scientists debate behind closed doors. If the universe contains planets more perfect than Earth, what kind of life has had the time and the conditions to grow there? And if it exists, could it already be far beyond us? Tonight, we follow the evidence, slowly, calmly, precisely. And it may take us further than anything you've ever imagined about life, and about our place in the cosmos. You hear the phrase, habitable zone, and the idea sounds comforting at first. A simple ring of space where water should stay liquid and life should take its first quiet breath. But the more astronomers searched the sky, the more something unsettling appeared. The habitable zone was not the truth. It was only the doorway. Some planets inside this gentle ring were scorched wastelands. Others were frozen tombs, and a few that lay just outside the line showed mysterious signs of warmth, chemistry, and stability. That was the first warning. The old map of life was smaller than the territory. Then came the question that disrupted everything. What if Earth is not the standard? What if it is only one version of life's possibilities, not the best one? A pause here, a necessary one. Because once that question appears, the universe changes shape. Suddenly, Earth stops feeling like the model and becomes one chapter in a much larger book. The data pushed this shift forward. New discoveries from Kepler and later from TESS filled the sky with unexpected worlds. With each one, the message grew clearer. The habitable zone was not a promise. It was only a suggestion, a faint outline, a probability that life might fit into or slip beyond entirely. Scientists began noticing patterns, planets in the right place that had long since lost their atmospheres, planets drowning under greenhouse heat, planets orbiting stars so violent that any hope for life would be erased again and again, and others trapped in tidal grips, forever frozen on one side and burning on the other. One thing became clear. Being in the right place was not enough. And that brought the next question. If the habitable zone is only the starting point, then what are scientists supposed to look for? Could the universe be hiding something better than Earth? Teams started examining new criteria: atmospheric thickness, geologic activity, magnetic protection, a star's lifespan, the smoothness of its light, even the rhythm of a planet's orbit. The deeper the search went, the more the universe seemed to open a door. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And in this case, the incredible thing wasn't a civilization or a cosmic signal. It was the possibility that Earth might not be the most welcoming home life could have. That thought carries a quiet weight. It suggests that Earth is not the ceiling, it is the floor. Researchers began to notice subtle advantages in other worlds: a slightly thicker atmosphere, a slightly stronger magnetic field, a slower rotation. Tiny differences that change nothing in normal conversation, yet change everything for evolution. Here is the turning point. If a planet only needs to be a little better than Earth to surpass it, how many of these better worlds could exist? As telescopes improved, more surprises appeared. Planets with nearly perfect orbits, planets with long-term temperature stability, planets orbiting stars that would live 10 times longer than the Sun. Suddenly, super-habitable worlds did not feel like a fantasy. They felt like a missing chapter of biology. Imagine standing by the ocean at night, listening to the tide breathe. That is what the universe feels like now. An ancient presence quietly revealing clues we were too noisy to notice. And scientists realized something essential. By focusing too narrowly on Earth-like conditions, they had ignored a spectrum of worlds that could offer more stability, more nutrients, more calm. Worlds that would not merely allow life, but nurture it. And once that realization lands, it cannot be ignored. If there are worlds that outperform Earth, then humanity's search is no longer just about survival. It becomes a search for potential, for future homes, for versions of life that might flourish beyond anything we have seen. No one expected the search to open this path, but it did. And what waits ahead is larger, stranger, and far more hopeful than the old models ever predicted. You move into the next layer of this story, and the shift happens immediately. The habitable zone was never enough. It looked simple, it sounded decisive, but it was only a doorway, never the destination. And here is the micro hook that changes the pace. Once scientists realized the doorway was too small, they needed a new map. A better one, a sharper one. That is how the idea of a new scale began. A scale not for where life can survive, but for where life can truly thrive. Superhabitability. The possibility that some planets may offer conditions more generous than Earth itself. For years, this idea lingered quietly at the edge of astrobiology. Too bold, too ambitious. But the data kept nudging the same truth forward. Quiet at first, then louder, until researchers had no choice but to formalize it. They needed a measurement, a way to quantify the subtle advantages that make a world more stable, more patient, more nourishing. And here comes the next micro hook. When you give something a number, you make it real. The Superhabitability Index asked simple but unsettling questions. How stable is the climate? How long will the star remain calm? How thick is the atmosphere? What does life need if it wants billions of years, not millions? Earth scored 0.829. A respectable score, a strong one, but not perfect, not untouchable. And that single number forces a pause. Because if we sit below perfection, then something must sit above us. What exactly makes another world outrank Earth? To understand it, imagine the index not as strict math, but as balance. The age of the star, the thickness of the air, the steadiness of the climate, the tectonic heartbeat beneath the crust. Whether minerals recycle slowly or too quickly, whether warmth lasts long enough. You do not need equations for this. Only intuition, and intuition reveals Earth's limits, mass extinctions, climate swings, solar threats, geological resets, all natural, but not ideal for uninterrupted evolution. A superhabitable planet smooths these edges, a stronger magnetic field, a thicker atmosphere, a calmer climate. Small changes, but they compound. Here is the next micro hook. Because the astonishing truth is how little it takes to surpass us. 10%, 15%. Minor shifts creating major outcomes. Scientists began to spot planets that fit this profile. Orbiting older, steadier stars, holding moderate temperatures, slightly larger than Earth but not enough to become hostile. That tiny increase gives them richer atmospheres, warmer interiors, longer tectonic lifespans, subtle gifts that biology can use. One researcher described it best. Life needs a home that does not rush. A world patient enough for growth. A world kind enough to avoid catastrophic resets. If patience is part of the formula, then many stars already surpass our Sun. stars that live billions of years longer, stars that give lifetime to become ancient. As the index expanded, perspective shifted. Earth became one data point among many, not the best, not the worst. Simply a workable model, a beginning, not a benchmark. A scientist once said, "The universe is under no obligation to make sense to you, and it is not obliged to place the best worlds near us either." That thought leaves a quiet echo. We evolved on a world good enough for oceans, forests, and consciousness, but maybe not good enough for life at its fullest potential. Another micro hook emerges. If nature can produce better conditions, then what kind of life rises there? How deep? How complex? How old? The index was never meant to diminish Earth, it was meant to widen the search, to release us from the narrow idea that Earth is the mold. The index suggests a generous universe, a universe where rich biology is not unique, only rare. As the models improved, certain planets began to outshine Earth on paper. Better stability, better climates, longer evolutionary windows. Some looked like oases, calm, balanced, protected. And that brings us to the final micro hook. Because once you realize that superior worlds exist, even in theory, you cannot help but wonder what lives there. The index is not just a measurement, it is an invitation to imagine life older than ours, deeper than ours, more refined than anything Earth has allowed. And the search is still in its beginning. You move into this next idea quickly now. Superhabitability is no longer a distant theory. It becomes real the moment you learn Earth's score. 0.829. Good, but not great. That number changes everything. It suggests a quiet truth scientists once overlooked. Some worlds may simply be built better. Here comes your first micro hook. Because the pattern that reveals this advantage is shockingly small. Size. Not a massive difference, not a giant planet towering over Earth, just 10% more radius, a touch of extra mass, barely visible if the two worlds were side by side. And yet that slight increase reshapes a planet's destiny. Gravity holds the air longer. Weather calms. Temperatures drift more slowly. Stability becomes the silent rhythm life can depend on. It feels almost unfair. How can something so small matter so much? But the models repeat the same answer. A thicker atmosphere, a stronger magnetic field, more internal heat. These super-Earths hold their balance with ease. Earth does it with effort. Here, a soft awareness rises. Earth tries its best. Other planets may do it naturally. Your next micro hook appears in motion. Picture these worlds turning under deeper skies, oceans that hold warmth longer than memory, forests that grow without the constant threat of climate whiplash. Life there has time. It has patience. It has room. Suddenly, 10% is no longer a measurement. It is a feeling, a kind of cosmic generosity. Scientists did not reach this conclusion quickly. They tested the physics again and again. Too big, the world suffocates. Too small, the air escapes. But the 10% window remains the sweet spot, a planetary balance hidden inside the numbers. Then comes the quiet hook. If these worlds are naturally more stable, what emerges after 8 or 10 billion years? Something older, something wiser, something Earth could never sustain long enough to see. But a perfect planet is not enough. Every world needs a star, a partner that decides whether it thrives or collapses, and that leads to the question hanging in the air. What kind of star makes this 10% miracle truly come alive? The next micro hook sharpens the moment. The answer is not our sun. The sun burns hot and fast. It grows brighter with time. It sends radiation storms across space. Beautiful physics, difficult biology. In a billion years it will trouble our oceans. a gentle reminder of Richard Feynman's words. Nature is not obliged to make your life easy. But some stars do make things easier. Smaller, cooler, deeper in temperament. The orange dwarfs, stars that burn with patience, that live tens of billions of years, that offer long, calm epochs instead of violent youth. That belongs to the next chapter. For now, the focus remains on the planet itself. Imagine standing on a world 10% larger than Earth. Gravity presses gently. The horizon curves differently. Clouds drift in thicker air. Time feels slower here. Even the chemistry shifts. A warmer beginning keeps oceans liquid longer. A thicker atmosphere protects against future extremes. This is not excess, it is moderation. A planet built for endurance. And now the final micro hook. If a 10% difference creates all this, how many of these worlds are waiting in the dark? How many already hold life older and deeper than anything Earth has known? The answer is unknown. But the possibility reshapes everything. These worlds might be the true reference for life. Earth may be the exception. And once you see that, the next question calls you forward. Because the perfect planet needs the perfect star, and the universe may already have them. You arrive at the next truth quickly now. Some planets become superhabitable not because of what they are, but because of what they orbit. And this is where the search sharpens. Because the perfect world means nothing without the right star. Here comes your first micro hook. The ideal star for life is not the sun. It never was. The sun burns hot, ages fast, shifts more than life prefers. It lights our world, yes, but it also rushes us, pressures us, forces evolution to sprint rather than wander. And when astronomers compared it to other stars, the realization grew impossible to ignore. Better parents exist in the cosmos. Orange dwarfs. Their light rests between red and gold. Subtle, steady, patient. They shine with a calm that stretches for 40 billion years or more, 4 times longer than the sun will ever endure. You pause, because that single fact changes everything. Life on Earth has had 4 billion years, complex life only a fraction, intelligence barely a blink. Now imagine a star that gives 10 times more time, 10 times more stability, 10 times more chances for life to deepen. Your next micro hook rises here. If evolution never had to restart, what could it become? Orange dwarfs offer something the sun rarely provides, a climate that remains calm for eons. Red dwarfs live longer, but punish their planets with violent flares. Yellow stars burn bright, but die young. Only orange dwarfs sit in the perfect middle, warm enough, stable enough, gentle enough. Their light is an invitation, not safety, possibility. You picture such a star rising in the sky of a superhabitable world. A muted glow, a patient warmth, oceans that keep their heat, atmospheres that refuse to collapse, life unfolding in long, unbroken arcs instead of chaotic bursts. And the next micro hook lands softly but with weight. Earth's story is full of resets. But what grows on a world that never resets? Scientists modeled biological time under these long-lived suns. Less ultraviolet damage, fewer star storms, more geological calm, environments that mature instead of restart, forests that could evolve for 20 billion years, coral reefs older than continents, minds shaped not by urgency but by time. Einstein's words settle naturally here. The important thing is not to stop questioning. And orange dwarfs force new questions. If life has had 10 times more time, how old could intelligence become? How refined? How deep? But the story grows more intriguing. Planets in the habitable zone of orange dwarfs orbit closer than Earth does. Their years are shorter. Their skies shift in different rhythms. Their tides sculpt diverse climates. Complexity without chaos. Variation without destruction. Your next micro-hook appears because when complexity meets stability, evolution becomes a symphony instead of a struggle. Astronomers now see orange dwarfs as the prime hosts of superhabitable worlds. Their longevity gives life room to breathe. Their calmness shields young ecosystems. Their light nourishes photosynthesis in familiar wavelengths. They are nature's slow architects, shaping worlds patiently. So you return to the central question, not 4 billion years for life to grow, but 40. What does life become when given that much time? The answer waits behind those quiet orange stars, and that possibility reshapes every assumption you carry. On a world warmed by an orange dwarf, evolution is not a race. It is a meditation. And intelligence feels less like an accident and more like an eventuality. Your final micro-hook rises like a tide. Somewhere out there, orbiting a star older than our history and calmer than our sun, life may have already walked far beyond our beginnings, and those stars are waiting for us to find them. You arrive at the next truth quickly now. A perfect star is not enough. A world is only as alive as the air wrapped around it. This is your first micro-hook, because a planet's atmosphere is not background, it is destiny. Scientists began imagining an atmosphere just slightly richer than Earth's. 25% oxygen instead of 21. A tiny change on paper. A tectonic shift for life. With that oxygen level, forests grow faster, insects grow larger, animals breathe easier. Fires ignite more readily but burn in patterns that renew instead of destroy. The planet becomes more energetic, more vivid, more alive. The next micro-hook rises here, because oxygen alone does not transform a world, but oxygen paired with warmth does. A global temperature just 5 degrees Celsius warmer than Earth reshapes everything. Not a scorched world, a greener one. Warm enough for humidity to climb, for forests to spread, for plant life to saturate continents instead of clustering into pockets. On such a planet, growth is the default. Decay is the exception. You picture it, a world wrapped in gentle moisture, morning fog stretching for hundreds of miles, valleys braided with rivers that never fully dry, mountains coated in layered ecosystems from base to peak. Earth knows fragments of this richness, but not the sustained version, not the eternal version. And here comes your next micro-hook. Earth brushed against this possibility once, then lost it. During the Carboniferous, oxygen soared near 30%. Forests expanded into near continents. Insects reached sizes that feel mythical. But Earth could not hold that balance. Geological cycles shifted. The atmosphere fell back. These lush worlds are not fantasies. They are equilibria Earth once tasted. Scientists realized the ideal atmosphere is not exotic. It is simply stable. A long-term partnership between oceans, minerals, sunlight, and a world slightly larger than ours. A world with more gravity to anchor the air. A world warmed by a patient orange dwarf. A world where this balance could last billions of years. You feel a pull of curiosity. What rises in forests that never stop expanding? What creatures evolve when energy is abundant? What intelligence forms when the world never forces collapse? Another micro-hook tightens the moment, because in a richer atmosphere, evolution has more pathways, more raw material, more time. Then comes the question scientists began asking. Are these worlds theoretical? Or have we already glimpsed them through starlight? Telescopes turned to exoplanet atmospheres. Light passed through distant skies. Spectral fingerprints revealed moisture, warmth, stability. Some even suggested oxygen-rich chemistry. Not proof of life, not even close, but far from barren. This is your next micro hook. The question shifts from could such worlds exist to where exactly they are hiding. Planets around orange dwarfs show signs of deeper atmospheres, more heat retention, water stability that spans geological time. The ingredients of a world that breathes more deeply. You see it now. A sky tinted by thick air, clouds trailing long and slow, forests without edges, oceans that barely change over millennia. Life on such a world would not simply grow, it would flourish. If biology has billions more years and far more energy, then its creations may exceed anything Earth has ever carried. Complexity layered upon complexity. Here, the physicist Victor Weisskopf whispers the reminder that fits the moment. In science, there are only solutions. Whatever the answer, it will always lead to more questions. These green superhabitats generate questions faster than we can answer them. Your final micro hook rises like a soft breath. If such atmospheres are real, where are these worlds? Are they already in our catalogues, waiting for deeper instruments? Or are they orbiting stars we have not yet learned to see? The story pauses here. Not from uncertainty, from anticipation. Because the search for the first true candidates begins next, and the worlds that may fit this profile could be closer than we think. You enter the domain of real planets now. No speculation, no theory. Actual worlds, orbiting actual stars, carrying the first solid hints that superhabitability might not be just an idea. And here comes your first micro hook. Because the moment the search moves from models to names, everything becomes real. Kepler 442b, Gliese 12b, GJ 251c. Cold labels, yes, but behind each name is a world that may already surpass Earth in ways we are only beginning to understand. Kepler 442b was the first to stir the scientific world, comfortably placed in the habitable zone of an orange star. Slightly larger than Earth, slightly steadier. Long before superhabitability was a formal concept, this planet was quietly hinting at it. Its orbit balanced, its star calm, its temperature moderate. Nothing dramatic, but everything promising. Then the next micro hook arrives, because Kepler 442b is not the exception, it is the preview. Gliese 12b came next, far closer to us, only a few dozen light years away. A world at the edge of habitability, perhaps cool enough to hold its atmosphere and warm enough to cradle oceans. A planet close enough for us to study in detail rather than guess from a distance. Its star is gentle, its orbit quiet, and the data, though early, suggests a world with real potential. You feel the shift, not fantasy, evidence. This leads into the next micro hook. Because Gliese 12b is more than a candidate, it is a test case. If we can read its atmosphere, we can read dozens more. The path forward widens. Then attention turned toward GJ 251c. Slightly larger than Earth, slightly warmer. Orbiting yet another orange dwarf whose lifespan outstretches the Sun by tens of billions of years. Not enough information to declare anything, but enough to suspect everything. Together, these planets reveal something subtle. They are fragments of a larger pattern. One offers the right size, one the right temperature, one the right star. Not complete alone, but meaningful together. Your next micro hook takes shape here. Because when fragments begin to align, you realize the universe is not sparse with opportunities. It is generous. You pause. The scale settles in. Millions of planets, thousands of stars surveyed. Only a tiny fraction understood. And already, 3 worlds rise above the noise with traits that echo superhabitability. It brings back a line from Eden Philpotts. The cosmos is full of magical things, patiently waiting for our wits to grow sharper. These planets are part of that magic, not myth, not hope, reality. Scientists began comparing them more closely. Kepler 442b for its stability, Gliese 12b for its nearness, GJ 241c for the age and calm of its star. None perfect, all promising. Together they form the first constellation of super-habitable potential. But the story does not remain at the planetary scale. Something deeper emerges, something tucked inside their systems, their stars, their orbital rhythms, their planetary siblings. Here comes another micro-hook. Because the planets are not the only clues, their systems whisper too. Kepler 442b lies in a quiet stellar neighborhood. Gliese Arsabi circles a star calm enough for precision measurement. GJ 251c may belong to a multi-planet system with delicate gravitational balance. These are not random, they are structural, architectural, hints of how super-habitable worlds arrange themselves in the cosmos. Which brings you to the final micro-hook. Because behind these first candidates, scientists began noticing an even stranger possibility. Entire star systems where multiple planets might be habitable at once. A harmony of worlds, a chain of opportunities, a structure Earth has never experienced. These first planets are not the destination, they are the introduction. The edge of a pattern waiting to be revealed, and beyond them lies a system unlike any we have found. A place where habitability does not belong to one planet, but to many. That is the next chapter, where the mystery sharpens, and the universe becomes less familiar than ever. You enter one of the strangest discoveries in modern astronomy, a system that forces scientists to rewrite their expectations, because here, the universe does something we never thought it would. It puts not one habitable world in reach, but several. This is your first micro-hook. 1 star, 7 planets. 4 of them potentially warm enough for oceans. TRAPPIST-1, a tiny star barely larger than Jupiter, glowing like a red ember beside the sun's flame. And yet around this faint light orbits one of the richest planetary systems we have ever found. 7 worlds, each roughly Earth-sized, packed so closely together that the entire system could fit inside Mercury's orbit. It should not exist, but it does. Scientists describe it as a cosmic nesting doll. Worlds tucked shoulder to shoulder. If you stood on one planet, the others could rise in the sky like swollen moons, bright enough to paint shadows across the ground. Their orbits are locked in resonance, each tugging gently on the next, creating a rhythm so precise it feels like music. Your next micro-hook arrives here, because when a system behaves this delicately, something unusual is happening beneath the surface. The first shock was its age. 7 or 8 billion years old. Older than Earth by a staggering margin. Old enough for life to begin, collapse, begin again, and still have ages left to evolve. The second shock came from the composition of the planets. Rocky, solid, familiar. Not gas giants, not frozen spheres. A family of terrestrial worlds formed from the same primordial dust. But the star at their center complicates everything. TRAPPIST-1 is a red dwarf, long-lived but temperamental in its youth. Red dwarfs often erase their inner planets with violent flares, so scientists feared the worst. Atmospheres stripped, oceans boiled away, a system full of scarred, dead worlds. Then came the next micro-hook. The data refused to fit the assumption. Some planets showed signs of thick atmospheres, others of atmospheres transformed, not erased. A few displayed spectral hints of water vapor or carbon dioxide. Not proof, but possibility. The James Webb Space Telescope sharpened the picture. Starlight passing through these atmospheres carried patterns both familiar and missing. Some worlds looked bare, others layered, others hinted at chemistry we do not yet understand. TRAPPIST-1 was no longer a simple question. It became a puzzle with 7 pieces. Scientists began to suspect the system represented something deeper. A snapshot of planetary evolution stretched across multiple worlds. Some planets stripped early, some rebuilding atmospheres through volcanic outgassing, some retaining enough air to shelter oceans. 7 chapters of a story we have never witnessed anywhere else. This is your next micro hook. Because TRAPPIST-1 does not offer one test for life, it offers 7. And then came the larger realization. TRAPPIST-1 may not be unique. Red dwarfs across the galaxy seem to form compact chains of rocky planets. Worlds born in clusters. Worlds that evolve together. Worlds that might share material, share impacts, even share life. A cosmic archipelago. If even one of these 7 planets hosts biology, the odds for life in the universe rise dramatically. It would mean nature does not create habitable planets sparingly. It makes them in groups. Heisenberg captured this feeling perfectly. Not only is the universe stranger than we think, it is stranger than we can think. You imagine standing on TRAPPIST-1e or 1f, the star glowing dim and red. Neighboring planets rising enormous in the sky. A sense not of isolation, but of belonging to a family of worlds. These planets may trade atmospheres through volcanic plumes, trade microbes through ancient collisions, trade histories through gravitational touch. And this becomes your final micro hook. Because if life can move between these planets, then TRAPPIST-1 is not a system. It is a cradle. A place where life could spread, diversify, and evolve across multiple worlds instead of one. 7 worlds, 1 star, 1 mystery still unfolding. And through their atmospheres, we have already heard the first faint hints. They are whispering, and we are finally close enough to listen. You enter one of the most fragile frontiers in astronomy. Not planets, not stars, but signals in their air. This is your first micro hook. The first hints of life out there may not be messages. They may be chemistry. The James Webb Space Telescope acts like a stethoscope pressed against distant skies. Starlight passes through foreign atmospheres, breaking into thin bands of color. In those bands lie fingerprints, oxygen, water vapor, rare chemicals that should not appear without something stirring them. The cosmos does not shout, it whispers. Tiny dips in starlight appear, small bumps in the data. Nothing loud, nothing dramatic, just consistent enough to make scientists lean closer. Oxygen on one world, water vapor on another, strange gases in proportions that do not quite add up. Your next micro hook rises quietly. On Earth, oxygen is not stable unless life is constantly renewing it. The signals JWST detects are fragile, unsteady, almost ghost-like. But patterns begin to form beneath the noise. Patterns that feel less like random chemistry and more like maintenance, like something tending the air. Imagine standing beneath one of those skies. Clouds carrying moisture across continents, light filtering through an atmosphere rich with potential. The first breaths of a world beginning to move, and this leads to the next micro hook. If something breathes there, what form does it take? Some researchers imagine simple life, microbes in warm oceans, colonies drifting in shallow seas, chemistry gently assembling itself into self-sustaining patterns. But others ask a larger question. What if these worlds are older than Earth, older by billions of years? What if life there has had more time, more experiments, more evolution, more chances to leap forward? Here, Stephen Hawking's words echo with new weight. Intelligence is the ability to adapt to change. On a stable world with a long-lived star, change comes slowly, predictably. Intelligence there might look different from ours, less reactive, more patient, more deeply woven into the planet that shaped it. You pause, because this reverses our usual assumptions. Maybe intelligent life does not build metal or light. Maybe it perfects harmony instead of tools. Your next micro hook arrives in a single, unsettling question. What if the faint signals we see are not accidents, but the atmospheric equivalent of a heartbeat? JWST cannot confirm this, but it can highlight anomalies. Oxygen levels too high for geology alone. Water vapor arranged in cycles. Exotic gases appearing in ratios that defy simple atmospheric models. A few worlds begin to stand out. TRAPPIST-1e, GJ486b, and others not yet famous, each showing hints, not proof, but hints that encourage deeper scrutiny. Scientists describe this process as reading shadows on moving water. You infer far more than you see. You trust the ripples to carry meaning. And now the next micro hook tightens. If simple life exists, has it had more time than us? More stability? More natural advantages? Picture evolution without mass extinctions, without ice ages, without asteroid resets. Imagine biology refining itself for 10 billion years. What would that look like? Would it create civilizations, or something quieter, more integrated, nearly invisible to telescopes? The narrative sharpens, because the signals we detect are not calls, they are consequences. No radio, no lasers, no artifacts, just chemistry. Your next micro hook settles like a low note. The absence of technology does not mean the absence of intelligence. Perhaps these civilizations choose silence. Perhaps they grow inward instead of outward. Perhaps their greatest achievement is equilibrium. If so, their signature would not be machinery. It would be balance. A planet whose atmosphere behaves as if tended by something older than we can imagine. This final micro hook forms around the central question. Are these atmospheric patterns geological? Are they biological? Or are they something in between, shaped by life that evolved far longer than ours? The data is faint, the answers unfinished, but the possibility hangs there, steady and persistent, a whisper carried in starlight, and we are only beginning to hear it. You enter the most unsettling possibility in the entire search, a possibility more provocative than signals or technology. A possibility so quiet it almost feels wrong to say aloud. What if the greatest sign of intelligence is not noise but perfection? This is your first micro hook. Because a perfect planet is harder to explain than a loud civilization. As scientists analyzed distant atmospheres, a pattern began to emerge. Not bright, not dramatic, but deeply strange. Some worlds carried climates too steady. Ratios of oxygen and carbon dioxide too balanced, orbital paths too smooth over geological time. Even the surface composition appeared oddly uniform, as if erosion, volcanism, and chaos had been softened for eons. One anomaly is chance, a cluster of them is not. The second micro hook lands here. Nature tolerates chaos. It rarely sustains long-term precision. Yet these planets showed stability that defied models, greenhouse cycles that corrected themselves, temperatures that hovered in narrow ranges, no sharp swings, no catastrophic resets, as if something had been guiding the system. Not recently, not loudly, but steadily. Researchers first assumed natural equilibrium. But equilibrium rarely lasts millions of years unchanged. So another hypothesis appeared, a quiet one, a careful one, that perhaps we were looking not at activity but at legacy. The long shadow of an intelligence that matured beyond machines, beyond industry, beyond the kind of signatures we expect. The next micro-hook tightens the idea. If a civilization becomes ancient enough, would it leave monuments or balance? Climate simulations offered another clue. The orbit of one world remained nearly perfectly circular. Planetary orbits typically wobble under gravitational nudges, but this one did not. A curve too precise for randomness, almost as if nudged back into place multiple times across deep time. Spectral readings added more mystery. Elements on the surface appeared unusually even in distribution, not geometric, not artificial, but optimized in a way geology rarely accomplishes. The kind of distribution ecosystems might eventually create if allowed to grow without interruption for billions of years. This leads to your next micro-hook, because perfection, sustained for ages, demands an explanation. Scientists call it planetary management, not dramatic terraforming, not megastructures, but slow, steady adjustments. The way coral reefs engineer oceans, the way forests regulate humidity, the way microbial life once shaped Earth's atmosphere before complex organisms even existed. Now imagine a species that has survived long enough to move beyond crisis, beyond growth, beyond conquest. A species that learned to shape its world the way a gardener shapes a forest. Subtle, continuous, invisible at a distance. A civilization so old that its technology no longer looks technological. A civilization so integrated that its planet becomes its body. You pause here, and the words of Neil deGrasse Tyson drift back. We are not only in the universe is in us. If that is true for us, it would be true for them. Their intelligence would not sit atop their world. It would run through it. Scientists remain cautious. They remind us of false positives, of limited data, of the seductive pull of wishful thinking. But even they agree that some planets look too stable to dismiss outright. So the question becomes sharper. If a world appears too perfect, how do we know whether it is shaped or simply rare? Your next micro-hook sits exactly here. A perfect planet might be the most advanced form of communication ever conceived. No beacons, no broadcasts, just a world that has been tended across billions of years. A world tuned into long-term harmony. A world speaking through stability. Some theories suggest that truly ancient civilizations no longer build machines. They become them. Their presence dissolves into weather, climate, chemistry. Their influence becomes indistinguishable from the planet's natural rhythms. If so, then the atmospheric balance we detect might not be accidental. It might be the message, a signature of patience rather than power. And this final micro-hook closes the thought. If we one day confirm such a world, we will not just discover life. We will encounter a civilization that has lived long enough to master its own planet completely. A civilization that survived every stage we have yet to face. A civilization so mature that harmony became its final technology. And then the question turns back to us. If they shape their world so perfectly, what will they see when they look at ours? The story stops here for a moment, because some answers must arrive slowly. As slowly as the civilizations that may already be waiting in the dark. We end our journey here, standing at the edge of everything we understand. And in this quiet moment, Earth feels different. Not diminished, not forgotten. Just no longer singular. Because the universe does not stop at worlds like ours. It shapes older ones, gentler ones. Worlds where life might unfold not for billions of years, but for tens of billions. Perhaps these planets are not destinations at all. Perhaps they are reflections. Hints of what life becomes when time is abundant and the light is steady. So the final question is not scientific anymore, it is human. If a world more perfect than Earth truly waits out there, would we step toward it? Would we trust ourselves to begin again on a planet designed by nature to embrace life even more generously than our own? Or would we pause at the threshold, aware that beyond that distance lies not only discovery, but a future larger than anything Earth has ever allowed? The universe has opened the next chapter, quietly, patiently, holding the page for us. And whether we choose to turn it will define who we become.